You ready to go, crew?
Let's do.
Cameras go. All right. All right, well, welcome everybody to this talk about forward progress guarantees. We're going to talk about forward progress guarantees in C++, but actually not just C++. The reason is a lot of languages de facto import the C++ abstract machine. Not a lot of languages go out and define, you know, what is memory, or many don't even define their own memory model, and many don't define their own forward progress guarantees either. What happens for a lot of languages is somebody builds a front end on top of an LLVM, and without realizing it, they've just brought the C++ abstract machine under their programs. Okay, so the rules here apply to languages in general, although C++ has some very specific wording for C++ facilities, and I'll tell you where that all activates. Okay. My interest in forward progress guarantees, like I remember pretty clearly when it began. I was working on CUDA, and we had just shipped CUDA 1.1 with atomics. We had started with a pure parallel programming model that did not have any atomics, and without any atomics, you can't get into trouble. And then at 1.1, we did a very well-meaning thing. We offered atomics with the intention that people would use them for reductions, but immediately people started using them to write synchronization. And neither the programming system nor the hardware were able to handle it. So if you went on Stack Overflow and you searched for CUDA, lock, or mutex, what you would have is pages of results. Every one of them is somebody saying, hey, I wrote this code with atomic exchange or with atomic cast, and I don't understand. I froze my GPU and Windows restarted the GPU. All right, so who am I? I've been a GPU architect for a fairly long time, since 2002. You guys probably have used the GPUs I have worked on. I currently work in platform architecture at Apple on Apple's GPU, on the programming model. And I'm the chair of SG1, Concurrency and Parallelism. Okay, so we're going to visit every facet of progress in C++, bar none. We're going to visit every corner, and I'm going to tell you where the defects are hiding right now. And if people want to write papers, you're welcome. Okay. But before that, I'll give you a quick introduction to the theory of progress. And what I mean by this is covered in a seminal paper by Herlihy and Shavit called On the Nature of Progress. But I'm only going to give you the little bits that we need before I show you build up the examples from C++. Okay, so the first term that we need to know is this idea of a scheduler. The scheduler is a part of the abstract machine that your threads run on, and the scheduler makes guarantees to threads. This term, forward progress guarantees, refers to those guarantees made by the scheduler. That's what we're talking about. Okay, and so the scheduler will say some conditions under which threads eventually execute operations. And there's more than one statement schedulers can make. And in fact, in C++, we have 3 different schedulers with very different guarantees that have a big impact on what code you can write. Okay, so that's step 1. There's a scheduler, and it makes a statement of guarantees. The term live lock has a very formal definition. It's not just, oh, my program has hung, it's live locked or deadlocked. The formal definition of live lock is that you wrote a program whose assumptions exceed the guarantees made by the scheduler. So I'll give you an example. Here's the scheduler, and its guarantee is at least one thread executes its next operation. And I wrote a program above where one thread sets a flag and another thread pulls on the flag, that is, it repeatedly loads the flag. This exceeds the guarantees of the scheduler because the scheduler says at least one of the threads. It didn't say all threads. So it could pick thread 2 over and over and over again. And thread 2 loads the flag and it's not the right value. And then the scheduler picks thread 2 again and it loads the flag and it's not the right value. And it never picks thread 1. So with a guarantee as weak as the one at the bottom, I cannot write code like what I described at the top. I get a live lock. Okay, a deadlock is code that goes beyond the maximal guarantee. There is such a thing as the maximal guarantee, a scheduler that promises that all threads at all times eventually execute their next operation. And a lot of people like to think that that's the only guarantee that's valid, but this is the maximal guarantee. If I write code that exceeds the maximal guarantee, then I have a deadlock. And so here, for example, both my threads are polling, and then after seeing a flag, they'll set another flag, and they switch on which flag. This program can never finish because thread 2 never sets flag Y, so thread 1 never sets flag X, and so therefore thread 2 can never clear, right? Okay, so that's a deadlock.
But how is that beyond maximum guarantees?
I'm sorry?
How is that beyond maximal guarantees?
A scheduler that provides the maximal guarantee does not execute this program to completion. It's not that this deadlocked program makes an assumption that could possibly be satisfied. It's unsatisfied.
Because of a cycle.
Yeah, because of the cycle. Yeah, exactly. Yeah.
So in the same cycle, if we have try logs, so
Yeah.
then deadlock gets converted to live log, right?
If you, I mean, it depends what you do. So if you try lock, and you, what are you going to do? You're going to try again?
Yes.
No, it's still a deadlock. Yeah, there's no scheduler that could possibly resolve your program. If you, I mean, you're just saying, you're just describing what's inside of the poll here. If I replace polls with all of the code that would be in the poll, that doesn't make it executable.
But doesn't deadlock also mean that two threads are not even making any kind of progress? And live log means that two threads are making progress, but I'm like, they are running, but they are not able to make progress.
No, so from the point of view of the forward progress guarantees, and actually I'll have a couple more example of how C++ connects to that. From the point of view of the forward progress guarantees, a program with a deadlock in it is constantly performing steps. It's just none of those steps make the program complete. And I'll show you on a graph if you want to hold that thought for a minute. Tony.
Okay, I was going to like lead up for you.
Yeah.
Because those threads are doing their next operation.
Yes.
The next operation is check the flag again.
Yes.
So they are doing stuff.
That's
they
right.
are executing.
That's right.
But there's
Yeah.
no progress.
So from the perspective of the scheduler, it feels like progress should be made. From the perspective of the overall algorithm, progress is not made. Both live lock and deadlock are felt the same, by the way. It just feels like a hang. It just means my program got here, and then it just kept busily doing things, but it never finished.
But instead of poll, if I change it to a mutex,
Yeah.
so it would sleep instead of polling.
No.
No.
We will see. We will see when we get in the formal definition of blocking in C++. That blocking. I mean, I'm prefetching what's on the slide in the future, but let's do it right now so we can move on. Blocking is defined as repeatedly attempting to take a step. Yeah.
Is live logs synonymous with starvation?
That's an interesting question. Let's say yes.
Yes.
Yeah.
Conditional
All right.
yes.
Now, when we have tasking abstractions in our libraries and programming languages, it makes things pretty fuzzy. So I was talking about threads a moment ago, but let's say that I launched two tasks and I launched them on some parallel 4 type of library abstraction. Even though the library is running on the C++ scheduler, even though a parallel library might be implemented using threads, and even though the scheduler grants threads maximal progress, my library abstraction can actually get in the way of that. And we are going to dive pretty deep into this over the next hour. So I'm just telling you what we're going to be talking about. Okay, so I'm launching 2 tasks. And what the tasks do is they invoke a barrier, arrive and wait. It'll depend on which guarantees actually make it through my library, whether this live locks or not. Okay, so let's now derive C++ from first principles. Okay, I'm going to show a bunch of code examples. I will say in general, none of my code is particularly good. This is all slideware. You shouldn't write this. There's great libraries out there that do what my code is going to do. I want to point out that I will put a red X if that code has UB, and I'll put a yellow X if it's merely a terrible idea. Okay. Okay, so let's start with single-threaded code. before we build up to threads. And we'll also build up terrible threading first. Okay, so here would be my litmus test for single-threaded code. This litmus test here represents all single-threaded programs that have ever been written. They don't include this. They've got other things, and then they do anything inside of main, but they haven't included those things. That's a single-threaded program. Great. I'm going to represent all of the programs in this talk using a graph of events. And so this is one of the most exciting ones. I invoke main, and then that is sequenced before the anything comment, and that is sequenced before the return from main. That's how we comprehend a single-threaded program. Great. It's got no races, it's got no forward progress issues, but it gets no free lunch. Yes?
It has data races.
It does?
Interrupts.
Signals.
Yeah,
Interrupts are
with
defined.
signals.
Yeah.
Yeah.
Signals are defined as having data races.
Thank you.
Nerds night.
Yes. That's great. That's great.
Contribution.
Yeah. I do want to say one good thing about the single-threaded program, which is that the single-threaded program might still use accelerated libraries in here. And actually, even though I'm the chair of SG1 and all I do on the committee is anything to do with threads and concurrency and parallelism and atomics and races and synchronization and all of it, please don't use any of it. If you can use none of it, don't. Use accelerated libraries as much as you can. There are, especially nowadays, as silicon becomes more and more heterogeneous, vendors put a lot more effort in domain-specific accelerated libraries, and the quality of that generally exceeds what is worth you attempting to recreate. And so you can get a free lunch with single-threaded code if you use accelerated libraries. And I think that that's perfectly reasonable to do.
And,
Yes.
and this code here could have parallel execution
Inside of the library? Well, it depends.
inside of just the main because it could use vectorized instructions, right? I mean, you just write a loop.
In C++, the auto-vectorizer needs to be imperceptible. It needs to be hiding under as if.
Yeah.
So I write single-threaded code, and that's all I need to worry about.
Okay.
Okay. All right, so let's add some threads to this. And we're going to do it wrong a bunch of ways so that we can get to the point where we can ask an interesting question. Okay, so I'm going to add a thread. And here, I'm just creating this thread. And what the thread does is that it has a statement A. It assigns 1 to data. And then I've got some other statement at B. And then I return data from main. Great. So this code has a bunch of problems. So we're going to start with the graph. Interestingly, at least, it's got 2 threads. So we have 2 chains of sequence before, each starting with an invocation. So we have the invocation of main, then in sequence before, a JThread constructor, a JThread destructor, B, although those are probably not sequenced here. It synchronizes with relation from my JThread constructor to the invocation of the lambda sequence before evaluation of A, sequence before its return. Great. We don't yet have forward progress issues, but the reason we don't have forward progress issues is we've got a bunch of problems.
Question?
Yes.
On your drawing before, it showed up as a J thread.
Oh, and here it's a thread. Slide bug. I meant thread.
And different behavior.
That's right. We're gonna use JThread in later slides. I'm sorry?
Stop token is the difference.
Yes.
The
It's a slide bug.
Instructor behavior is the difference.
You're getting to my point of like 2 slides from now. So it says thread. Okay, everybody? It says thread.
Your eyes are lying to you.
That's right. It says thread. Okay, so the first problem is that at our thread destructor, we're going to call terminate. Because it's an unjoined, undetached thread. So it's going to call terminate. So that's no good. I said unjoined, undetached. Well, I could detach it. Well, that's worse in a way. Now I have 2 problems. The first problem is that I have a data race between the assignment of 1 to data and the read of data in the return statement. And I have another one. And the second race is that I have a use after lifetime end where this thread's lifetime can go beyond main and it could attempt to dereference data, which is on the stack, whereas data's lifetime is ended when we return from main. So that's no good. All right, I said unjoined, undetached, so we could join it. We could do that. And here's a yellow X. Yeah, I used threads, but I wrote a serial program on 2 threads. So that's not great. I didn't actually get any parallelism here. So I'm not getting a free lunch by doing something like that. Okay, so that's not great.
You're buying someone else lunch here.
Yeah. Now, I also could do the exact same thing with JThread, which avoids the terminate and it avoids the data races. That's all good. But, you know, JThread actually bought me into this serializing behavior. So that wasn't great either. So now finally, we're going to get to a form of my litmus test where we could talk about progress guarantees, where I finally got some concurrent statements here. I've created a scope. My JThread's lifetime now is, and I've named it, my JThread's lifetime now is that scope. It has a statement at A within the JThread and a statement at B in the surrounding scope. Those 2 things are concurrent. So now we can talk about concurrent execution. Okay, so we covered wrong ways to use threads. Now we've made it to a point where we can have a conversation about the main topic. So let's talk about concurrent progress guarantees. And for that, I'll give you my definition of concurrent. I'll say there are 2 polarities on how people use concurrent and parallel out in the wild. In SG1, though, this is the polarity. When somebody comes to SG1 for the first time with the wrong polarity, the whole group corrects their polarity, and henceforth we go with the meaning that C++ uses. Okay, so my personal definition is that concurrent tasks eventually observe each other's effects. They are actually running at the same time, and they are given eventuality guarantees from the memory model that if they make an effect, it is eventually visible to the other one. Okay, so now the question is, so we had some concurrency earlier. So now the question is, we have one blocking operation here, and it's the JThread destructor. Does it eventually unblock? The answer is going to be yes, but that's because it gets the concurrent progress guarantee. Okay, so now here's the corrected graph. We've got a synchronizes with edge going from the JThread constructor to the invocation of the lambda. We have a synchronizes with edge from the return of the lambda to the JThread destructor. And now we're going to annotate this up with our formal definitions that build up to the concurrent progress guarantee. So we're going to need 3 definitions. We're going to need to know about threads of execution. We're going to need to know about the abstract machine steps. And we're going to need to know when threads take steps. Okay, so step 1, I've colored them now. I have 2 threads of execution. You might say, that was so obvious. Okay, yes. The definition of a thread of execution, we're going to revisit it at the end of the talk because it's not as clear as what I'm just about to say, is that it begins with the invocation of a top-level function, and it includes the flow of control from that point on. Okay, so here I have 2 threads of execution. They begin with the invocation of main and the invocation of the lambda, and then it's the flow of control from there on. Okay, the sequence before relations in this case. So those are our threads of execution. Great. The abstract machine steps. This is one of the most important things to know about this entire conversation here. Okay. There's specific things that are considered a step. Performing an operation that synchronizes is a step. Accessing an atomic is a step. Accessing a volatile is a step. And here, so here you have them all. And termination of a thread of control is a step. So here, I have my 2 threads of control. I see the operation that synchronizes, the JThread, is a step. The operations that return are steps. There's the blocking operation, which is one of the kinds of synchronizing operations that is a step. And then, as I mentioned a bit ago, there is a rule that says that a blocking operation is treated as if it performs an indeterminate, potentially infinite number of internal steps, which is easy to remember in your head as it's the moral polling loop. Now, whether there's actually a polling loop there, the standard does not say, right? So a mutex might be implemented with efficient blocking. But from the perspective of the C++ abstract machine, that mutex lock function that blocks is as if it is constantly doing a try-lock, right? And that is a step. Okay, and then finally, when do they take steps? Well, threads of control, threads, eventually execute a step. So both the blue region, everything within the blue region, we always eventually perform the next step. And everything in the green region, we eventually perform the next step. And that's what we're going to now write more formally in a bit as the concurrent progress guarantee. All right, there is a should thrown here. So should, in the C++ standard, should always be scary to you because it means we know what we wanted to spec, but, well, actually, there are reasons why sometimes an implementation might not be able to implement the spec. So instead, we use normative encouragement, which is should. Okay. So here there's a should, and I think you might have an intuition for why there's a should. On many operating systems, you can set thread priorities. And on many operating systems, those priorities are heeded. And that's not everywhere. So for example, on Windows, there's pretty much nothing you can do with priorities that will cause Windows to completely starve a thread. However, on Linux, you very much can. And so all of these rules here, as it pertains to C++ implementations on Linux, for example, mean this is going to be true under nominal conditions unless you went and messed with thread priorities. Okay, so here we go. The J thread, it should eventually unblock. Great. And that's our concurrent forward progress. We're going to build out our menu of forward progress guarantees over the next few minutes. The concurrent forward progress guarantees is threads eventually execute their next step. And that starts from the moment a thread is constructed. So the thread might not even have performed its first step yet. But if the thread exists, it eventually performs the first and all subsequent steps. Okay, so now we're going to look at using this wrong. This is the maximal guarantee. So we're going to write a graph with a deadlock in it. Here I have a semaphore. And to release the semaphore, I need the J thread to finish, but the J thread acquires the semaphore. Okay, so this is the graph where the dependencies are. And you can identify this from the graph as this is obviously deadlock because of the cycle. From a forward progress guarantee perspective, what's going to happen, though, is the scheduler is continually giving these threads the opportunity to perform steps, as they do, but they are spending all their steps in the blocking operation. Okay, so it's not that this program lost its forward progress guarantee, is that it cannot complete with its forward progress guarantee. Okay, and that's a deadlock. All right.
But it's not going to be.
Why is it termed as a forward progress guarantee if it is a deadlock? Just because it is doing infinite amount of steps, it looks like it is forwardly progressing, but it is not actually. Because it's not.
From the point of view of the implementation is doing everything right. It's constantly scheduling that thread. It's constantly giving it a shot at doing something. The computer underneath, unless you only use platform synchronization primitives, and only if the platform has deadlock detection. In general, implementations can't know whether you deadlocked. The implementation provided you a forward progress guarantee, and you did something not useful with it. Okay. All right. So we have concurrent progress and the maximal guarantee, and that's, and if we were talking about C++ 11, we'd be done, because C++ 11 doesn't have any other facilities. It has stood thread, it has the unnamed thread that runs main, and both of these get the concurrent forward progress guarantee in hosted implementations. In freestanding implementations, it's implementation defined what they get. Okay. So now we're gonna build what it was introduced in C++ 17 and is going to continue to be relevant in other facilities that we add in the future. Okay, so let's talk about parallel progress. So we talked about concurrency. Here's my definition of parallelism. Parallel tasks never observe each other's effects. This would be the definition of pure parallelism. Is parallelism in C++ pure? Not always. There's a lot of pragmatism that gets into it. And the intuition for remembering this one is parallel lines don't intersect.
But at that
Yes.
point, why would you create threads that could be just another process?
No. The parallel tasks don't crosstalk with each other, but they take their inputs from the program and return their outputs to the program, right? They start with a program state,
So you're talking
they do
about-
computation on that state, and then they produce an output state, except during the parallel computation phase, there should be no write-write or read-write conflicts between the threads there. And this is pure. Like, this is pure parallelism. C++ is not that pure. We'll talk about like the pragmatism that was folded into it.
Yeah, like it's probably my question is, there's no guarantee that they will observe, or there's a guarantee that they won't observe.
Yeah. So in pure parallelism, if you attempt to communicate between tasks, you violated the programming model, and we should give you UB.
Yeah.
Yeah. Okay. However, you're all. I'm gonna go right to the pragmatism. You're all pragmatic C++ people. You know that computers implement parallelism on top of concurrency. When I go and use a parallel programming API, it is actually implemented on top of threads and CPU cores, which are concurrent and can observe each other's effects. So we have a name for this, which is this one. There's no debate. It's industry-wide. We call it discovered concurrency. When you write using a parallel programming model, and you write code that will have some degree of communication between the threads, even though you couldn't know a priori which threads would run at the same time, there are many idioms where you can work with whoever is here. Yeah. So that's called discovered concurrency. And I could start a discussion of the parallel progress guarantee by starting from the pure end, but I think for C++, it's better to start from the pragmatic end. So what we're going to do is we are going to progressively build our way to a parallel programming library, and we're going to ask ourselves, what sort of progress guarantees does that library have? Okay, so we're going to start with something you probably shouldn't do. There's no yellow X here, but it's a bad idea. So I have some number of tasks. Now, I said discuss here. Like, tasks could be, I have 10 things to do. Tasks could be, I have 11 million things to do. Okay, so now I'm going to create a vector of JThreads. You should have alarm bells in your head.
Yeah.
11 million JThreads might not be a great idea. And I'm going to construct a JThread into each one of these. And so at the comment here, parallel work, that's whatever. It's whatever my parallel work is. And then at the end, I destroy that vector, which destroys all the JThreads, which joins all the JThreads. Okay, so this is a cutesy way to have a big fork join. Okay, let's draw the graph with 2 tasks, because I don't want the graph to be huge. Okay, so it looks similar to what we had before, except we have 2 JThreads, each one of which is a step to create. I have 2 lambdas that are invoked. They are separate threads of execution, because a thread of execution is all the control flow from, and I'm missing some sequence before edges here. Okay, so that's my graph. What progress guarantees do I have here? And my test is I'll do what I did earlier at the very beginning of the talk. I said, what if I do a barrier arrive and wait? Is that supported? And the answer here is going to be yes, because I'm using full threads. So if I write the barrier, both lambdas arrive, both lambdas wait, the synchronizes with edges. They cross, but they don't form a cycle. They go in the right direction. And so this is fine. So our very baby's first parallel programming library, a vector of JThreads, has concurrent forward progress. So we haven't yet discovered anything new. Okay, but you know that we're not really in free lunch territory just yet. So if I look at how efficient that is, like how much time am I spending on a per task basis, I'm going to get a curve where as I add more threads, the time to do the total amount of work relative to serial goes down. But then I'm going to hit this point where I've saturated all of the cores, and then this line actually goes up a little bit. And that's because once I've put a JThread on every core, I'm just asking the computer to do less useful work in the middle of my work, right? It's doing context switches between the JThreads. And, you know, here I made it linear, but it might not be linear. And I've done nothing good for small tasks. So for large tasks, that amortization was pretty good at the beginning. But for small tasks, I might never really make it much better because the cost of creating a JThread is pretty high. And so if the cost of my task is on order the same or even smaller than creating a JThread, I'm just creating even more work for the computer to do. So now we get into the business of building a parallel programming abstraction. Why do people who talk about parallel programming don't talk about spinning a bunch of threads? So we're going to go over four things to worry about. We're going to start with amortization. Okay, so, well, launching a JThread per task with 11 million tasks was not a smart idea. So how about we launch a JThread per hardware concurrency unit, which should be cores in principle. And now I'm going to push a for loop into each task. So each JThread is going to loop over some number of tasks. And so if I launch 2 of them and I had 4 tasks, then each one loops twice. Yeah, makes sense. Okay, so here's our graph. So we have 2 pieces of parallel work per Lambda invocation. And my amortization now is going to be much better. It's going to decay. It's going to go down even for small tasks, because if I have 11 million tasks and 2 JThreads, then each one does 5.5 million tasks. So that's great. It's going to trend. It's going to trend right. You're going to get a bit of this sawtooth thing, which is once I've given 1 task to every core, when I ask the task to one of the cores, I've doubled the amount of time it takes to finish this by creating a tail effect. Okay, we're not yet worrying about it, but we will worry about tail effects real soon. Okay, now, do I have the same progress guarantee? It's a bit of foreshadowing because the answer is going to be no. So if I put my barrier in here again, now remember my barrier counts tasks, not threads. So I create a barrier of tasks, and I do arrive and wait inside of my loop here. We can draw this as a graph for 4 tasks and 2 threads. And these are all the synchronizes with edges that we have to have. And there are many problems here. There are many cycles you could create, not just one, but I'll pick one. I'll pick maybe the most intuitive one, which is that I'm waiting for subsequent iterations in the other threads. And we can't get there because in the previous iteration, we're waiting. And then we spend all of our time in blocking steps. Now, this is not yet a scheduler. I launched the threads. The threads are in my code. The loop is in my code. I'm using the operating systems, I'm using the abstract machine's concurrent forward progress guarantee. It's not yet a new scheduler, but we're getting there. So this is a deadlock, and it's a deadlock for the reasons I just gave. We see the threads, we see the loop, we see the dependencies. It's entirely in our code. There is an important point here, which is that whether we're going to judge it a live lock or a deadlock, or whether we're going to judge whether we have a forward progress guarantee issue or not, will depend on the line where we cut the notion between the program and the implementation. So for now, we have started something that if it was a scheduler, it would have lesser guarantees, but it's not part of the implementation just yet. Okay. All right. So what kind of task, what sort of guarantee would it have? Well, if a task has taken a step, it eventually takes all of its steps. Because in my Lambda, I invoke a task, then I invoke another task, but I don't interleave these tasks within one of the Lambdas. So I call the first task, and once I execute an effect in the task, I'm running the code of the task. And the code of the task is running on the thread, so it's getting the thread concurrent forward progress. So once a task is executed a step, it eventually executes its next step. And at least n tasks eventually execute their first step. That is the breadth of the number of threads. If I have 2 threads, then at least 2 tasks execute their first step. And when a task finishes and I go down to 1, I immediately snap back to 2. Right? Like when a task on the first Lambda finishes, then I go run the next one.
Is creation of a task also the first step of the task? Like I can have a task and immediately do a wait inside it. So that will itself be a step. So which is the first step in this case? Creation of a task, will that be a first step or that wait?
No, it's the wait. If I go back to a graph, let me go to a non-terrible graph. This one. This thread of execution has exactly 1 step. And it's this one. If there was a step inside of the parallel work, then the first step would be here. The invocation is not a step.
Okay.
It's not on the list. Yeah. Okay. So, all right. Let's talk about tail effects. The sawtooth thing, and then there's a whole other dimension to this. That when I look at my tasks serially, it might be that they're not all exactly the same length. Like imagine I do a key search into a map. If it is found, it'll come back quickly-ish. And if it is not found, I'll have to exhaust the maximum distance, to figure out, right? So sometimes we have tasks that are really short and tasks that are really long. And if I just dole out the tasks by their index, I might end up with a problem like this, where these bars have the same number of tasks on them, but some of them got all the short ones, and some of them got all the long ones. And so the utilization of my computer goes down after a bit. At first, it's great. And then I'm down to 2 threads running, and then I'm down to 1 thread running, and I need to wait for that before finishing my parallel batch. So we're going to fix this, and it's going to have a slight effect on our progress guarantee as well. The way we're going to fix this is instead of doling out tasks with a predetermined index assignment, we are going to steal the tasks from a queue. We're going to say there's this atomic that counts the number of tasks, and each thread will repeatedly go atomically decrement that counter, get a unique number out, and say, I'm running that task. If one thread pulls all the easy tasks, then it'll come back to the atomic more frequently and pull more tasks. If one thread gets all the long tasks, the opposite happens. Okay. Now, when I build it like this, there's an interesting, the red arrow that I want to point to is when I build it like this, there's an interesting thing that happens where the number of threads in the group can be completely erased now. This code works perfectly well with 1 thread, 2 threads, 10,000 threads, doesn't matter. Okay, so I can get an execution that looks like this. 1 slow task, 3 quick tasks, and better performance. And I don't necessarily need to know if it's hardware concurrency width to make this work. Could be any width. Okay, so because it could be any width, then we're weakening what the guarantee might be. The guarantee might be that at least 1 task executes its first step. If there's only 1 thread in the group, then only 1 task might take a first step. But this will still finish the batch as long as there's no synchronization between them, right? Okay, so now I'm going to take this idea of the work-stealing set of threads of an unknown number of threads, and I'm going to wrap this into a thread pool API. I'm going to imagine a thread pool API. I create a pool, my thread pool, and my thread pool has this run function where I want to run some number of tasks, and I pass in the lambda with my parallel work. And then when I join the pool, let's say it joins all the threads. The same thing, basically it's the same code from previous slides, just repackaged. Yeah, repackaged. That is starting to be a pretty plausible parallel loop library in people's code. Okay. All right. Now, if I create my thread pool locally like this, I am going to set myself up for oversubscription. And we need to tackle this problem before we could put a parallel abstraction in the C++ standard like this. Okay. Okay, so here's the oversubscription case. Let's say now I have an outer parallel work and an inner parallel work. And for the outer parallel work, I instantiate my thread pool and I go pool.run. And that created a vector of JThreads, probably the size of hardware concurrency. And then inside, I have some more parallel work. It's got this two-dimensional thing. So I create a thread pool, again, creating a new vector of JThreads per JThread. And now I do some parallel work over ij. So this is what I just did. Taken in isolation, every occurrence of my thread pool has the amortization strategy on the left, because we did it right. But when I use it in my program, in composition, I end up with the behavior on the right. So I'm going to get a mix of these two behaviors. So instead, what I'll want to do is have a global thread pool, big shared thread pool, and then I'll just append both levels of tasks into this thread pool. And now that solves my oversubscription problem. However, I have created myself a starvation problem. So let's go take a look at what that starvation problem might be. Now, this one, I think we're going to need to spend a little bit of time reading it. Okay, so, and this is, even if there wasn't a red X, there'd be a yellow X here. This is the kind of code that you write when you want to find out where things break, not when you want to do useful work. Okay, so I'm going to start by creating in my code, not in the thread pool, in my code, I'm going to create a thread per task. And then I'm going to turn around and take the work and push it on the thread pool instead. And I'm going to put in there a barrier arrive and wait. Should that work? Well, if the barrier of arrive and wait was in the JThread itself, it would work. But I put it on the pool, and we know that the pool promises to only run at most one task. And as a result of that, this doesn't work. This hangs. At the very least, it hangs. And I'm starting to say that we're getting to a live lock here because we pushed the thread pool as part of the implementation. But the problem is, how can a C++ program ever trust a global thread pool if the program itself had 4 threads and each thread had work, and when you did local reasoning within those threads, that work does not have a deadlock or a live lock. But when I compose it as a result of having a global thread pool, it does. Now, my solution to various performance problems made it impossible for me to reason about my program as anything but global. And global reasoning is untenable, so not acceptable. So we're going to add one more ingredient, and then we'll be done figuring out the parallel forward progress guarantee. Okay, the one more ingredient is in vernacular called boost blocking. In the standard, it's called blocking with forward progress delegation. And here's how it works. So first, we introduce a way to block on a set of parallel threads, tasks. When I give work to my thread pool, it can't just be a void returning thing. It can't say, thank you, and then give me such a weak progress guarantee. if it gave a really strong progress guarantee, that interface might be acceptable. But because it has a weak progress guarantee, we're going to make it return a kind of a handle. It's going to say, here's a handle to refer to this bunch of tasks you just gave me. And then when we block on this handle, we're going to take an action. And there's a couple of actions that we could take. We could start preempting the tasks. You know, if we had a preemptive scheduler, our scheduler is a for loop. It's not preemptive. So we can't do that. But if we had given it to an operating system and the operating system had reified lightweight threads for this, the operating system could say, oh, you've blocked on this, so let me start preemptively context switching to upgrade the progress guarantee. Or we could start adding threads to the pool. Like when you block on it, start adding threads until things unblock. And there are operating systems that work like that. What we are going to do is we're going to do something called child stealing, which is when the parent context that created the work takes part in the task stealing scheme. When our thread will block on this handle, it will start running the same code that the worker threads were running. So it starts stealing from the queue, but it only steals its own work. So it does forward progress delegation to the child work that it created. Okay. So here's what that might look like in my code. I've got my pool.run, and now it returns some kind of a handle. I'm not telling you what the API of my handle is or the name of it, so I capture it by auto, but it does have a drain function. So I enqueue my task of 1, and then I call task.drain. And what happens here is I may have started with a thread pool that has only 1 worker thread in it, and maybe I had 8 tasks, let's say. So that 1 worker thread can only execute 1 arrive and wait. But when all of the parent threads arrive at the blocking point, arrive at the drain, they will donate themselves to the thread pool only for their child work and only for the duration of the child work. So that the thread pool will appear to have 9 threads in it and 8 things to do.
So the work at this point is actually no longer executing at the thread pool because the thread pool has everything blocked.
Yeah.
But the individual J threads that scheduled the work in the first place, they execute the work.
Yes.
Okay.
That's right. So this is to build your intuition of how forward progress delegation might work. In practice, you know, you're not supposed to know how C++ implementations work. You get a C++ implementation. You're not supposed to look under the hood. It does whatever it does. It could do the other schemes I mentioned, but here is a really intuitive way to think about what happens when a parallel API can be blocked on and the standard mandates forward progress delegation.
So this delegation is happening from the child to the parent, right?
The parent is delegating its progress to the child. The parent has a very strong progress guarantee here. It's a J thread, so it has concurrent progress, it has maximal progress. And then its child does not have maximal progress, it has parallel progress, which we're going to get the definition in a bit. So when the parent blocks, it promotes the progress guarantee of the child group to concurrent, but only one at a time. Like it makes sure that at least one of them makes progress.
Because it is waiting for the child to complete, which means that child has to do the next step. So
yes.
That unless it doesn't do, then the parent will keep on blocking.
That's right. That's right.
So when we were counting in the example, so we gave that object to the parent. So why were we adding 1 extra thread? Like you said that 8 and then you said that 9. It's just using the parent for doing the same thing. So why are we counting that as an extra?
Well, so I'm saying at the point where all of the parents have called .drain, one of them was lucky and its child thread had actually been scheduled on a worker.
Right.
The remaining 7 did not. Okay. But when all 8 call .drain, they will all make themselves available to run work that they created if it's not progressing.
And the next parent will be waiting for the next set of child threads which would start executing. Each one only delegates progress to its child. So you can't have
thread 7 pick up the work from thread 3. That, I mean, you potentially could build a system like that, but then proving to yourself that you've implemented forward progress delegation correctly would be more difficult. It's easier if you restrict the effect of the parent showing up to only its children.
And how this drain over here is different to the normal p-thread join that we see in C code.
Oh yeah, it is not.
same.
It's not a join. No, the bottom one is, but this one isn't. The bottom one drains the whole pool, and that's just that would be just a join. But this one here that waits on this specific task. I'm sorry, the shadow is not great, but this one here that waits on this specific task, that can't be a p-thread join. The work may not have a thread to run on.
Okay, so yeah.
So what the parent does is it calls the same function that the worker threads themselves call to participate in the work stealing scheme. So it becomes a worker thread temporarily until its children are done, and then it returns to what it was doing.
So yeah, conceptually, the pool, the tasks would not have, each of the tasks would not have a thread to run on.
Yeah.
So parent waiting on child to complete.
Yeah.
Over here is not one-to-one mapped with the join concept, because join is very much related to the thread instance.
That's right.
But conceptually, it's still waiting for the tasks, even though it is not having
It is.
a thread backed by to complete.
Yes, it is.
Okay.
Yeah.
What I'm struggling to see like how useful this incrementing guarantee is in practice, because I still need like all of the J threads that call the drain, right? So I can't just put arbitrary work on the thread pool that then waits for other worker threads. I still need in the end to have like enough things available that call the drain for it to complete, right? So if I imagine like an application, right,
Yes.
where just like arbitrary pieces start putting stuff on the thread pool that waits
Yeah.
for other stuff that has to happen on the thread pool,
Yeah.
right? Then I still need to be able to reason globally that I will never put so much on the thread pool that it will like block.
No,
all
you don't
this,
need to
right?
reason globally. No. So every parent is guaranteed that they will get the parallel progress guarantee of the next slide. They will receive a parallel progress guarantee for all of their children, regardless of what everyone else did.
Mhm.
And part of what provides this guarantee is that the parent will be given a blocking handle, and they will need to call that to know that the work is finished. And in the worst case possible, the parent runs all the child work inside of that.
Okay, so like the parent has to make sure that like all the work that I push, that
Yeah.
I could complete it in like within my single thread.
Yes.
And then then I see how.
Yeah, yeah. But earlier we cleared that the parallel progress guarantee might have only one worker thread in the limit.
Right. Yeah.
And-
yeah,
and
yeah.
Now I'm saying in the worst limit, that one worker thread is actually the parent.
Yeah. That I understand the reason.
Okay, so if we had a task scheduler here, then we've already settled on this thing at the top. Tasks that have executed a step eventually execute their next step, because every time I call one of the task functions, I execute that task function until it finishes on a thread. And at least one task, this is the previous guarantee that we had, now that we say that is blocked on, eventually executes its first step. Okay, and this guarantee is literally what parallel algorithms offer. So in C++17, here's again, an ugly version, not code you should write, just use the C++17 parallel algorithms. But if I was rolling my own parallel for each, this really short little bit of code would implement a parallel for each on my thread pool, right? So for slide purposes, I made this real ugly. A and B are iterators, C is a callable. I grab the distance between A and B, that's the index space that I need to run on, that's the number of tasks. So I send the callable, I call the callable with the ith next thing from A inside a lambda, put that in my thread pool. I get the handle that comes out of that, and I immediately call drain on it. This is parallel for. And it has all the amortization and the oversubscription avoidance and the tail effect avoidance, and it has forward progress delegation. It has all these properties that we described before by wrapping the things we have built so far.
Amortization in what sense?
If you give me 11 million small tasks, I don't launch 11 million threads. And in aggregate, because I loop over, let's say, I mean, this is one of the first things we covered in this section, right? So that the cost per task trends to the true cost divided by the number of active threads. Yes?
I assume you're missing the bracket or something.
Am I?
You're
Oh, yeah, I am.
missing a paren.
I'm missing a
Sorry,
paren.
paren.
Just before the dot drain. Yeah. All right. So that's our parallel forward progress guarantee. So that's 2 out of 3. Luckily, the third one will be much quicker. Okay. And now we can test again whether we have a live lock or a deadlock. Here I use my parallel for each. I'm using now something that looks like C++17, just respelled, a little bit uglier. I pass it an iota range, and I call arrive and wait. Does that work? Well, that does not work because we've exceeded the guarantees of the scheduler now. That's a live lock. We don't see the threads. We don't see the loop. It's not in our code. It's in the implementation code. The implementation made us a forward progress guarantee that is parallel forward progress. Parallel forward progress only promises to start one of the tasks, and my barrier needs all of the tasks. So that does not work. That's a live lock. But it's not a deadlock because if I had maximal progress, it would work. It would execute correctly. Okay. So let's look at weak parallelism, weakly parallel progress. So I'm going to go back to my definition from earlier. Parallel tasks never observe each other's effects. If you can never observe each other's effects, now I'm going to be pure. I'm going to be strict now. Before I said, we all know this is C++ and we're pragmatic and things run on threads and therefore you can communicate about it. Now I'm going to say if you make any attempt at communicating between threads, you're going to get UB. And you're going to get UB from the memory model and you're going to get UB from the forward progress model. Okay, so no discovered concurrency under pure parallelism. Okay, so now we can make some really strong assumptions. We can assume that all tasks are finite. They eventually finish because they're not allowed to block on anything. So there is a finite number of execution steps, and there's none of these potentially indeterminate loops. All right, and there are no critical sections. What I call a critical section here is a first visible effect, which precedes a second visible effect. That is in the program the assumption that if you see the first and you wait, you will eventually see the second. Okay, so there's both of these assumptions we can make, and as a result of that, I'm going to jump right to weakly parallel progress as a definition. We can just take the bottom rule, and we're going to say at least one thread that is blocked on eventually executes its next step. Note, I deleted the first one. If you've taken a step, I make no guarantee when you'll execute the next step. Okay, so down here, I'm just lumping all of the threads of execution into one yellow dotted domain, and I say, inside all of this, I promise to execute one step. Now, I could repeatedly choose this and never this. And so synchronization inside a set of threads that have weakly parallel progress is completely disallowed. You'll get live locks. Okay, because the progress guarantee is very weak. And that's actually very good for SIMD, GPUs, DSPs. If you're going to take code which looks like sequential code, like imagine you want to map a for loop to vector units. You have a lambda, it looks sequential, it is what each vector lane wants to do. But vector lanes are not full threads. Vector lanes are not preemptively scheduled. They don't have maximal progress against each other. If inside of that function, there's an if I want to take a lock, if I get the lock, I do this, else I do something else. And the way that the vectorizing compiler scheduled this is that it only chooses the losers of the lock and just keeps retrying for the losers to take the lock. They'll just repeatedly fail. And this is the reason why that very first thing I opened with, the deadlocks, the hangs on CUDA, it was because really what CUDA offered at the time was weakly parallel progress. And anybody who wanted to write a mutex was assuming, at a very minimum, parallel progress. So those people had exceeded, those code authors had exceeded the guarantees of the scheduler. You know, you start from, you encounter an upsetting thing, and you're like, oh, I think this should work. And then, you know, you spend the next 15 years like understanding the theory behind the thing. Okay. So we have parallel algorithms in C++ 17. If you use std execution par, you get parallel forward progress. If you use a std execution par on seek, you get weakly parallel forward progress. And there's a lot of things you can do with that. With par, for example, you can take locks. You know, earlier I couldn't put a barrier here because a barrier needs everyone to arrive at a barrier to synchronize. But with a lock, before you take the lock, you're not making any assumption about who else is here. You can make an atomic effect that takes the lock, and critical sections do work under parallel progress. They just don't work under weakly parallel progress. Even if they don't work under weakly parallel progress, you could still do a lot of things. Like in this algorithm here, I'm looking up a bunch of keys in a map. This is an example I like to use all the time. Like if you got some huge map and you want to look up 10,000 keys in a map, that's completely legit. You're not mutating the map, so there are no write effects here. There's no synchronization. The map is constant here. And I'm just going to do a bunch of lookups. This is perfectly good under weakly parallel progress.
In the strong guarantee, if you are taking the lock at one time only one would be progressing because of the lock. Right?
Yes. Yeah, that's okay. It does not exceed the guarantees of the scheduler.
It's a yellow X.
I mean, yeah, right. I mean, you don't, right. You don't want to write a sequential program split over multiple threads. But that batch of parallel work, it might have had really substantial work with only a small portion requiring the lock. That's perfectly good. Yeah. Okay. All right. I have a lot of loose ends. We're done describing progress right up to C++ 23. There's these 3 progress guarantees. You access them via parallel algorithms. And when you write code that's going to be invoked as part of these algorithms, you need to know what guarantees you're allowed to assume, or else you'll cause live lock. And of course, in a library setting, that could be very interesting. Let's say you write a library. Is it safe to invoke under weakly parallel progress? You kind of need to document that for your users. And if you're a library that exposes callables, callbacks, and you're going to run that on something other than threads, you need to tell users, I'm going to invoke your callables with parallel forward progress. They need to know that. Okay? All right. So the loose ends. There's, you know, as chair of SG1, I maintain in my head a bit, like, yes, we have a defect report list, an official one, but then there's all the little bits that, oh, in a meeting, something came up, we discussed, we're like, oh, that's not clear. And no one filed a defect, and there's no paper about it, but it consumes our headspace. People in SG1 consumes our headspace, remembering like sort of the ragged edges of the spec. So we're gonna cover that. But I want to talk with my favorite UB, because this is what a friend of mine sent me when I said I have a favorite UB. Would be a shame if something happened to it. And then
text you this image.
Yes, this is literally our messenger window. Yes. This UB is really important for implementation diversity. So let's talk about it a little bit. What it says is that every thread can be assumed to eventually execute a step. Many of you might know this UB as the prohibition on infinite loops, or the permission for compilers to optimize away infinite loops, right? While one semicolon. Compiler can remove that. Why? Because it's UB. Why is it UB? It's because if you write while one semicolon, your thread is not eventually executing a step, but it is required to. This requirement is placed upon the programmers because it is stated as an assumption all implementations are allowed to make. Okay, so what can I do with that? I can do really cool things with that. So it provides me, the implementer, with a proof that I don't need to prove. I receive the proof that A is finite and B is finite. And why are they finite? It's because they don't contain any steps. So whenever I do a thing that is not a step, it'll eventually be done. It will not have any polling loops or anything of the sort. Okay, so now what I could do is I could take my threads of execution and I can dice them up into what I'll call, for this conversation, threadlets. And these threadlets are segments of threads of execution that end in a step. And I am guaranteed to be able to do this over all programs. So the first threadlet is the invocation of main to the first step. And then there's B to the next step. And then 3' is its own step, is its own threadlet because it's entirely comprising of a step. Then there's the final termination step. Here, this is one step. The invocation of the lambda is a finite thing and is not a step. A is finite and is not a step. And the return is a step. So then I could build an implementation, and this exists for real. It exists in production, in the field, large volume. Implementations of the C++ forward progress guarantees on a non-preemptive computer. The computer can have essentially just fibers, and if the compiler indicates to the scheduler where the steps are, it can perform a fiber switch there. And yes, it means, yeah, when I do an atomic fetch add, that's a step, it needs to fiber switch. If I call a blocking function, that's a step, it needs to fiber switch. And if it visits all of the active threadlets, if it visits all of the threadlets where some task's PC is, it'll eventually correctly execute the program. Yes?
So my intuition for a step is still not very strong. But what would happen if I said that if I have a normal loop, that each iteration through the loop is a step?
You're saying that, or this is de jure by the standard? It is true.
If the standard would define it, that like
yeah, but it doesn't, right?
Yeah, like just hypothetical. If it would say that, like what would be the implications? Because then like whether we have the UB or not wouldn't play a role anymore.
Yeah. So if you this is sort of getting to that paper. If you modify the C++ standard to say that every iteration of a loop is a step, then these implementations that fiber switch at steps would be fiber switching an obscene amount.
Because
their performance would be destroyed.
Because you would really have to do a fiber switch with every iteration.
With every loop, everywhere. Yeah. Whereas these steps are actually pretty rare and coarse. Like how often, like in the grand scheme of things, what fraction of instructions executed in your program are synchronizing atomics? Like, right? Yes.
Going one back, the world as we know it is built on top of infinite message loops.
Yeah.
Are those UB?
It depends. Do they contain a step or no? And I think they do. Because if it's a message loop, you're like pulling a thing off of an OS queue. Yeah, you're doing a lot of things here that are actually steps. Like you've got some syscall, which you could just define as blocking on the OS. You've probably got volatiles or atomics. Getting a thing into your message loop from where the thing came from, you're fine. You're fine. It's really just for loops over non-atomic data with no synchronization, no volatile, no atomics, no sync.
And absent that, if they have an exit condition that may or may not be reached, is that enough to make them not UB? Because they may finish?
If they don't finish, an implementation that hangs your program is conforming. So they should finish. The implementation is going to assume it finishes.
So any synchronization primitive is a step?
Yes. Yep. Any synchronization primitive is a step. I mean, we did reduce, like, out of the trillions of operations in your program, we have reduced this to, the hundreds or thousands, which are just these. And when talking about forward progress guarantees, Everything else, you lump it into a box and you call it A, and I don't care what it does. Like, you could be like, you know, a billion lines of code. Don't care. Call it A. It's one step.
And it makes a lot of sense because at this point of synchronization primitives, that's when we can switch to the next task.
That's right. Yeah.
Because
That's right.
we know that at least till this point we are
Yeah.
consistent. It's a, I mean, like we'll not have undefined behavior after we switch.
Yeah. This undefined behavior, very dear to my heart. I'm sorry, Mike. Very dear to my heart. The ability, the permission to make implementations that are non-preemptive is very important, I think, for the diversity of the C++ ecosystem. So I am a little bit down with that paper, but it will be prosecuted. Okay. I'd like to talk about interactions with the memory model. You know, forward progress and the memory model are two separate bits of specification, but they touch in a bunch of places. So one first food for thought is that progress is like both the cause and the solution of data races. Like you wouldn't have data races if you did not have concurrently progressing tasks. And at the same time, you use your forward progress guarantees to build synchronization, which you use to remove data races. Huh. Think about that. Another thing is that there's two kinds of eventuality that are mentioned in the standard. The standard says that atomic effects are eventually made visible to other threads. But then the forward progress guarantee is all defined in like a thread eventually executes a step. Are these two eventualities in any way separately observable? And I think that the answer is no. If I made a computer that I swear it gives you maximal progress, but it has an infinite cache that holds atomic effects indefinitely, I think you might reasonably conclude that you didn't have forward progress guarantees because like you never were able to observe effects from other threads. You know, conversely, I could make a computer that makes effects visible instantly in 0 time. Speed of light wires with 0 caches to infinite speed RAM. But I don't give you a forward progress guarantee. Do your atomics actually make it to memory in 0 time? How could you tell? It would feel like the atomics are held back. So there are two eventualities in C++, and they are essentially inseparable. Okay. All right. The next thing is more a defect, and I want to explain it a little bit. There's this concept in the memory model world called Roche motels. And wait for it. They should not be a problem. Okay, but the standard doesn't say that. And the standard doesn't have any words that prevent problematic Roche motels. All right, so what's a Roche motel? So first of all, it's an American brand of cockroach traps. And they had a tagline that goes, roaches check in, but they don't check out. Okay. In memory model parlance, here's what a Roche motel is. So I have this very simple piece of code, and it has a critical section in it. It starts with acquiring a semaphore and then releasing the semaphore. And it's got 3 operations. It's got an operation A, B, and C. The very meaning of a critical section is that B, the effects at B, cannot be reordered above the acquire or below the release. The purpose of acquire and release is to trap B. Okay, however, you can check in. You can't check out, but you can check in. A and C can move into the critical section. Okay, now, for computations check in, but they don't check out. That's the Roche motel. Okay, now what if I wrote this program? This program has no bugs, it's fine. I've got 2 semaphores, and there are 2 threads, there's a J thread and main, and each one releases a semaphore and then waits on the other one. This has concurrent progress, maximal progress, so this is fine, right? No problem with this. So I'm going to express this as a perfectly fine graph. There's no deadlock here. The edges don't cross. Valid program. Now, when you look at the rules for Roche motels, and it says you can move things above a release or below an acquire, there's no special rule here that says you can't do that with atomics. And there's no special rule either that says you could move one atomic, or you could move 10,000 atomics, or you could move an indeterminate number, potentially infinite number of atomics. So I could roach motel like this. And then when this executes, it live locks. Or it deadlocks, actually. You know, there's no words in the standard that tell implementers not to do that. I've worked for more than one implementer who had to sit down and have the conversation of our company ships a major implementation of C++. Whatever shall we do about this? And then internally, we would express a rule that we would say that we can only optimize as if isolated for a finite time. You have to imagine a theory. When you optimize atomics, you have to imagine a theory that the world froze. This one thread had its operations execute inseparably as one atomic unit, and then the world unfroze. And the important bit is the finite. And when you have that rule, you can't move a potentially infinite number of acquires, right? And this is what happened in. Woo! I just lost the projection.
Okay. Start now.
Oh.
Computer guy?
No. The presenter view just came back.
I have your slides, so it's just waiting on the projector to hold them up. But they are feeding to me.
All right, there we go. So when we did this illegal roach motel optimization, what we did is we moved a potentially infinite number of acquires, and that's what we shouldn't have done. So if it was acquire steps here, so if it was just a load acquire, one load acquire, that would be fine. A while load acquire not equal 42, that is not fine. Okay. All right.
Why is it termed as optimization? Because we are checking in. So when we check in, the scope of the lock increases.
Yeah.
So it should not be termed as an optimization. It's like...
No,
The problem is A, B, and C can be reordered. And if they're...
Yeah.
Yeah, they are reordered, but the
That's fine.
effect from the
No,
outside
but if
world
there are
would
other
be...
atomics.
Well, the reordering of atomics, there are rules that prevent reordering of atomics. Those will be obeyed, but there's a lot of atomics that can be reordered. And yeah, so no, this could be highly profitable. It could be happening to your code. It's making it a lot faster and you don't know it. Yep. And the compiler might have some notion of like where the long memory latency arcs are. And by moving the acquire up, it's able to overlap memory latencies. And, you know, and as a result, it reasons, sure, moving a load of data at A under the acquire is actually better. And as long as it follows all the other rules, it's allowed.
So, but now the compiler needs to know that the acquire can have these infinite number of steps, right? So it needs to understand the semantics of the operation.
Well, so in general, it wouldn't be allowed. In general, if it's an external function and the compiler doesn't understand what's in it, then
it won't do it.
So in many cases, it won't. But from an abstract machine perspective, you have to imagine that all the code's in the same translation unit. It saw all of it. And that acquire there, as far as the compiler is concerned, it just sees that there's a loop over load acquires. It's the only thing it sees. Okay. All right. We're getting close. So let's talk about lock freedom a little bit. Lock freedom is not just programs that don't include mutex, although it is that. It's also using atomics that are lock-free. But that's not enough. You're not writing lock-free code formally if you're using atomic lock-free and express an algorithm that is not lock-free itself. And by lock-free, I mean it's got to be conforming to the weakly parallel progress. All right, if you meet all these three conditions, you're writing lock-free code. I actually really don't like people saying, I'm writing lock-free code, and then I see a loop, and they're polling for a thing. Yeah, no, it's not lock-free. Like, you didn't use a mutex, great. Maybe you used atomics that are themselves, each individual step lock-free. But that loop there, you're landing in an algorithm category that is termed starvation-free most of the time. Okay, so
most of the queues, lock-free queues, have that while loop and have that cast condition. That,
yeah,
so
That's okay.
that is also not lock.
no, hold on. The loop is inside the queue.
Like, well,
Like it depends what your pop interface is.
Yeah.
If your pop interface is always try pop, then and there's no pop, there's only try pop, then and try push, no push, no pop, try push, try pop, and there's no loop in the implementation of the queue, then the queue is lock free. What you do with it might still not be lock free. Like if what you do is while not push, try push, okay, you didn't write lock free code here, and that code would fail under weakly parallel. It would live lock. Because you're making an assumption that it eventually succeeds. What does that mean? It means that eventually some other thread makes an effect that makes this effect succeed. This other thread there, what relationship of forward progress do you have with it? If the relationship you have is weakly parallel, then remember the yellow dotted line. The scheduler can constantly schedule your try push and never schedule the other guy's pop, right? So lock free formally is also conforms to weakly parallel in addition to all of that. Okay. Oh, we just locked the projector again.
Now, is that a deadlock or live lock?
It's still running, I'm wondering. Give me a second. Of course, it doesn't run at the end, you know? And your computer's still feeding?
Yeah, but my computer doesn't feel the port because it has switched out of presenter view. It's giving me the slides that would go on the projector.
right.
Oh, and now presenter view just came back. So it means the port just came back to life.
I see it, it'll pop up there in a second.
All right. Okay, so when it shows up on the screen, we're going to have a piece of code that builds a histogram, and it builds a histogram over atomic signed lock-free. So it's lock-free. So that's all great. This is lock-free code. I'm using lock-free atomics, and I'm not closing loops. Great. Okay, except C++ tells us that sometimes lock freedom isn't lock free. And in the interest of time, I'm not going to make you read all of this. There's this like weasel wording that says, well, there are some computers with load, lock, store conditional, where actually if all the threads try to load lock at the same time, none of them can succeed. So if everybody's trying to do a fetch add, it's possible that the computer will be stuck in a mode where no one gets to do a fetch add, and it just burns heat. It just produces heat for an indefinite period of time. And we're going to say that that's conforming C++. And now that property is not lock-free. When C++ says lock-free atomics, on that computer, the actual algorithm category is obstruction-free. And then, if you go read that paper that I mentioned before in The Nature of Progress, and you read the definition of obstruction-free, is it says that these programs only work if there's a uniformly isolating history. And then it says, how do you do that? You have backoffs. C++ has this weasel line that says your entire view of the world might be that there's no such thing as lock-free. Everything is just obstruction-free. You should have backoff loops. And it tells you nothing about how or when. Like, for example, in this fetch add, the backoff loop would have to be inside the fetch add. I didn't write fetch add. So this is a little bit gnarly. I think maybe at some point in the future, we're going to need to just tighten this and say, look, from the point of view of C++ developers, they need to not know about this. And it's the implementer's job to figure this one out. Good luck.
Yeah, is that an enter? Is that inside a fetch add?
It'd be inside all of the atomics.
Yeah.
If you try it a bunch of times with load lock store conditional, you just progressively back off. And yeah.
Isn't this something that the standard should push to clarify? Because
yeah, everything in my loose ends section is like
embedded perspective. Like
yeah.
You need to know these kind of things, right?
Yeah.
Otherwise, you are not able to. You might be like not meeting your requirements. So, like this is something that in my mind can prevent also people from actually using C++ in embedded world confidently.
Yeah. Yeah, I think, well, I mean, in the embedded world, there's already a very big pile of factoids you're supposed to know. I think one of them would be an embedded where obstruction freedom is your lock freedom. You should express everything in terms of atomic compare exchange weak. Use nothing else, just atomic compare exchange weak. And then in all of your emulations, have a back off loop. And that would probably work. Yeah. Yeah. Yeah, we should clarify this. I think it will be a very interesting conversation when we do. Okay, let's talk quickly about atomics under par and seek. I haven't shown you a slide with atomics under par and seek, even though atomics technically can work under weakly parallel progress. And the reason for that is that par and seek is weakly parallel progress and unsequenced. And if you consider the layer cake of UB rules in C++, the unsequenced UB is stronger than atomics. It never says in the standard that unsequenced lock-free atomics are not UB. It says unsequenced effects that write are UB. And that just, by default, us writing no extra words about that includes atomics. Even though on any plausible implementation, lock-free atomics work just fine under par and seek. Okay, so this example that I had in the previous slide, the histogramming thing, it was lock-free code. And because it was lock-free, it is safe under weakly parallel progress. So in principle, this should work. But you have to put par there, not par and seek, as a result of that. So what should we do? Should we allow atomics under par and seek? Should we create a par weak, which is just weakly parallel progress, but not unsequenced? I had a thought that we could introduce a memory order that is very limited in what you're allowed to do with it. You're not allowed to synchronize with it, for example, and then say only that one is allowed under par and seek. So you could write reductions, which a histogram literally is.
Yeah. So in all these cases, you're writing an atomic, but you never look at that atomic from the other.
Yeah.
From the other.
That's right. Yeah. Yeah. So like a thought.
You're communicating to your program later after you
yes.
stop.
It's that you have like concurrent effects, but you're only interested in the final effect. Yeah. Okay. A quick word about magic statics. So magic statics are statics that have initializers and they're used in a concurrent context. I didn't put a red X or on this slide, meaning this static here under par and seek is, as far as the standard letter of the law, this is allowed. However, if I rewrite it with call once and I have the exact identical code that the compiler would have produced for the magic static, but now I have it with call once, that's not allowed. And I think implementations of par and seek actually don't function correctly with magic statics in them.
And this is talking across the two.
Yeah. It is synchronization. Yeah. So are magic statics actually allowed? The standard says nothing about it, so yes, but that's not intended.
Defect.
Yeah, that sounds like a defect. Okay. And then there's a lot of things that are unclear about threads of execution. So what is a thread of execution? Earlier, I used the definition flow of control starting from the top level invocation. Definition A is my favorite definition for thread of control, thread of execution, and that's what we should use everywhere. However, there are sentences in the standard that equate threads of execution with full threads. Thread, J thread, and the thread that runs main. And there's literally a sentence somewhere in there that says, that they are the same. But they haven't been the same since 17. And they have a lot of interesting properties that we might want to document. Okay, so I'll just quickly walk through those properties that we might want to talk about. And they're much more important if atomics are allowed, for example, under par and seek. As long as atomics are not allowed and you can't communicate, some of these properties don't matter much. But as soon as they are, and they are under par, it matters a lot. So here's a little litmus test where I grab the thread ID from the ambient. Am I gonna conclude that my threads of execution got different thread IDs? No, I'm not gonna conclude that. Well, first of all, because I'm sequencing them onto worker threads and I'm gonna get the worker thread ID. And so yeah, some number of tasks are gonna get the same thread ID, if only for that reason. But if they were communicating over atomics, they might get the same thread ID at the same time. Especially when talking about par on seek. If par on seek scheduled my tasks onto vector lanes, multiple tasks will come to the conclusion that they have the same thread ID at the same time. All right. Similarly, thread locals. Same thing as thread ID. Thread ID is just a special thread local in a way. So all of the thread locals, they might have the same one. And that could be a big deal. When people use thread local, one of the assumptions they're allowed to make is I'm not going to have any data races with other threads on this thing. Well, under par on seek, you might. Also, under par on seek, it might just not work at all. It might be that accessing that thread local makes your implementation fault. Okay. What about stack pointers? Stack pointers are really interesting because in a lot of implementations that are based on SIMD or that are on GPUs, the stacks are laid out in a completely different format. Instead of being, there's an address and there's a set of linear locations and my data is just written there. Instead, it gets interleaved. So lane 0 gets one word, then lane 1 gets a word, then lane 2 gets a word, and then it repeats, right? And the compiler knows the address assignment. And so the compiler makes your code just work. It might even make it just work with pointers, but it might not work when you pass a pointer between tasks because the other task doesn't know how to interpret your pointer. Your pointer only makes sense in your context. Okay, so are escape stack pointers usable? In C++, there is a paragraph that says yes. In C++, you can take the address of anything on the stack and share it with someone else. Okay. So of the loose ends, just to be clear, these I welcome papers. Yeah. And I think there's quite a bit of work. There's quite a bit of work to do here. We could have a smashing great C++ release for SG1 that just fixes those things and does nothing else. All right, so to recap, your code runs in the threads. Those threads run on a scheduler. Scheduler makes a guarantee to your threads. There's more than one kind of guarantee. It's not just the maximal guarantee. Okay, those guarantees are these. You've got concurrent forward progress, which is maximal progress, and that's what you always want to assume. That's great. You have it. From full threads and the thread that runs main and hosted implementations. And then there's parallel progress, where I don't promise how many tasks I will start, but I'll start at least one if you block on it. And of those tasks that start, they will have maximal progress until they complete. And then finally, weekly parallel progress, which takes your entire task, makes a bag of it, and executes eventually one step in that bag. Okay, and it's pretty important that you document what progress your code assumes. If you're writing a library in particular, you need to tell developers what you assume is beneath and what assumptions they can make above.
Is there a way to do that as a static assertion?
No. The problem about this is that it's an assumption about like the ambient ether the program is in. You know, it doesn't show up in code. It's not statically checkable.
We could make it a property, like a part of the type system of the function.
You could imagine rustifying this.
Yeah.
Where like base functions say what progress they assume, and then functions like it all gets built. Yes. But in C++ or C, no. Yeah. All right. Thank you.